At NTT Photonics Laboratories, we are developing a hybrid optoelectronic router combining the high speed of light and the functionality of electronics to solve problems of power consumption, throughput, and latency with electronic routers. The router consists of three components: an optical label processor, an optical switch, and a shared buffer. Let's look at the operation of these components by following an optical packet through the system. An optical packet consists of a label, which contains address information, and the payload, which is the content of the packet. The optical packet first enters the optical label processor. Here, the label and the payload are separated, and only the label is sent to an optically clocked transistor array, or octa. In the octa, the high-speed serial label is converted to a low-speed parallel signal, using the label itself as a trigger, and then it is recognized by a CMOS circuit. The CMOS circuit rewrites the label and outputs it as a parallel signal, which is converted back to a high-speed serial label by the octa and reunited with its payload. Next, the optical packet enters the optical switch. The optical switch converts the wavelength of the optical packet based on the address recognized by the optical label processor. The optical packet is then routed to the destination output port by passing through a cyclic frequency AWG. We have developed a wavelength tunable laser having low driving current, high-speed wavelength switching, and very little wavelength drift by incorporating a double ring resonator within the laser. In this way, most of the optical packets are forwarded with extremely low latency. However, if there are several optical packets bound for the same destination at the same time, one packet is stored in a shared buffer to create a time difference before sending it to the output port. In the shared buffer, part of the optical packet is sent to an optical clock pulse generator, where a signal optical pulse synchronized with the leading bit is generated. This optical pulse is sent to an optical pulse train generator composed of a fiber loop, which generates an optic pulse train matching the length of the optical packet. An all-optical serial to parallel converter converts the optical packet into low-speed parallel signals for writing to CMOS memory. First, this converter divides the optical packet and passes them through paths with different delays. Then, the optical clock pulse irradiates a semiconductor surface normal optical switch during the time window when all input bits have arrived at the switch. The switch only reflects the bits during this time window, converting the optical packet into a parallel optical signal. When it is ready to be transmitted, the packet written in memory is returned to an optical packet again by the octa and forwarded to the destination output port by the optical switch. The shared buffer is capable of high-level functions such as buffering for contention resolution, wavelength conversion, multicast routing for duplicating packets, QoS services, and 3R regeneration based on the TTL count. The hybrid optoelectronic router, which introduces new optical devices and new optical packet processing technologies, will realize environmentally friendly, large-capacity optical packet switch networks.